It's really, really.
Well, welcome everybody. Today we have the pleasure of talking about chaotic tides, as opposed to, your less chaotic tides. But mostly we have the pleasure of welcoming Michelle Vick, who is visiting us from Northwestern, and is an expert on many things about the evolution and dissipation of tidal systems, and I'll leave it at that, but welcome.
Thank you, Morgan. Thank you so much for having me here to talk about chaotic tides. So as Morgan referenced, I've worked on a variety of different types of astrophysical systems, from coalescing neutron star binaries, pre-common envelope systems. So if anyone wants to talk about those kinds of things later, I'm happy to discuss as well. But for the sake of telling a coherent story, I'll focus today on chaotic tides and hot Jupiter formation. So just so we all start off on the same page, when I reference hot Jupiters, I mean Jupiter-sized giant planets within about 0.1 AU, or maybe roughly 10 days. Those aren't quite the same, but close enough, with orbital period. And for warm Jupiters within the range of about 0.1 AU to 1 AU, so just a little bit further out. And these are some of the first giant planets first exoplanets that we detected, because they're so big and so close in to their host stars. But how they get there is still a little bit of a mystery. We think that you shouldn't have the materials and the conditions that you need to form those planets where we see them today. So there's a few broad categories of hot Jupiter formation theories. The first being in situ formation. So a protoplanet has migrated inward, and then it accumulates its gas envelope around where we currently detect the planet. And then the other two categories involve migration of a fully formed planet. So one type would be disk-driven migration, where the planet migrates through interaction with a protoplanetary disk. And the other, which you might guess from the color is what I'll be focusing on, is high-eccentricity migration. High-eccentricity migration is a two-step process. So the first step is to excite the planet onto a highly eccentric orbit, as the name implies. And there's a lot of different ways to do that. You can do that through planet-planet interactions like scattering, or through the influence of a companion, which I'll talk about a bit later. But once you have the planet on a very eccentric orbit, now every time it passes through pericenter, it has a very strong interaction with the star. And that raises tides on the planet that over time will dissipate. And the dissipation of those tides will result in the circularization of the orbit and shrinking the orbit down to a hot Jupiter orbit. The smaller the pericenter distance, the faster the circularization happens. But there is a bit of a catch here, because if it's too small, then the planet is just torn apart by tidal forces. So you want the pericenter distance to be small, but not too small. There's a bit of a sweet spot. There's a few advantages of this formation mechanism in terms of explaining observed hot Jupiters. One is that it naturally accounts for a pileup at a period that corresponds to a few Roche radii. So just by nature of needing the pericenter to be in a sweet spot, that sort of gives you a period range for the final hot Jupiters. It can explain a lack of nearby companions, although I think there's some recent work suggesting that there are some hot Jupiters that have detected companions, but many of them do not, which would be consistent with a more dynamic formation process like high eccentricity migration. And it can account for large stellar obliquities, which I'll talk about a bit more later. But various types of high eccentricity migration can result in a significant misalignment between the planet's orbit and the spin axis of its host star. A lot of previous work on tidal dissipation has used a parameterized treatment of tides, where tides are, you use kind of a tidal lag time, maybe, is one way to think of it. So here you have kind of the standard picture of the gas giant has a lagging tidal bulge. But there's a few problems with doing this. One is that oftentimes in order to have efficient migration, so in order for the hot Jupiter to form within the lifetime of the star, which you would need in order to see them, You have to assume that the gas giants are a lot more dissipative than Jupiter. And the formation fraction is significantly reduced by tidal disruption, by needing to be in that pericenter sweet spot. So a lot of planets that could migrate efficiently instead are just disrupted. And I hope to convince you that a more nuanced look at tidal effects can help to overcome some of these issues with standard theory of high eccentricity migration, and to talk about what kinds of predictions you would expect from this process with dynamical tides. So what we do expect in terms of the period distribution of these planets, the obliquity distribution, and what they look like as they go through the process of high eccentricity migration. What do I mean when I say dynamical tides? Well, different from the picture of static tides, when you have this very eccentric orbit with a close pericenter passage, the time scale for that pericenter passage is actually very fast and can be comparable to the dynamical time of the planet. So in that situation, instead of thinking of a static tidal bulge, it's more accurate to think of exciting oscillating modes within the planet each time it passes through pericenter. You could think of like ringing a bell. Each time the planet passes through pericenter, the planet has a set of natural modes at which it likes to oscillate. So those are the oscillations that the star excites. And when that happens, energy and angular momentum are transferred between the orbit and the modes in the planet. As we look at multiple passages, so the planet, if we use the analogy of a bell, is still ringing the next time it comes around, then the phase of the mode is going to affect the amount and even the direction of energy transfer when the planet passes through pericenter. So we can characterize this oscillation mode with a complex mode amplitude. It has a magnitude and a phase, and the phase is important when you pass around through pericenter again. And for this giant planet, the most important mode, it turns out, is just the fundamental mode of the planet. So the simplest mode, it has no radial nodes. And the reason why this is most important, there's a few. One of them is that the frequency tends to be pretty comparable to the frequency associated with the pericenter passage. So the fundamental mode frequency is sort of if you combine, the mass of the planet and the radius of the planet with the right exponents to get you the right units, and you get the frequency for the fundamental mode, roughly. And that tends to match up well with, for these systems, the frequency associated with timing of pericenter passage. And the second is that the overlap integral is large, meaning that the tidal potential of the star is efficient at exciting this type of oscillation in the planet. So we can write out an equation for how the mode amplitude should evolve with time and couple that with how the orbit should evolve with time. But one of the difficulties with that is that now you have to integrate over this very short time scale of the pericenter passage, and then also the much longer time scale of an orbit. And if you want to do long-term evolution of the system over many, many orbits, and that becomes numerically challenging. But fortunately, for a highly eccentric orbit, you can describe what happens to the mode in the planet with an iterative algebraic map, meaning that if I know what the mode, oscillation mode looks like just before one pericenter passage, I can do a simple algebraic calculation to tell you what it should be the next time the planet comes around. And that speeds things up significantly. There's a few parameters that determine how the system will evolve over time. The most important is the energy that's transferred in a single pericenter passage. So this is the change in mode amplitude squared. You can think of energy as related to the mode amplitude squared. It tells you how much energy is in the oscillation. So you can think of that also in terms of a phase shift. So if you have a change in energy, that corresponds to a change in the orbital period. And then if I multiply that change in orbital period by the frequency, at sigma, of the mode, now I have a phase shift. So this phase shift from energy transfer is going to characterize what happens long-term in the system. If it's small, as you can imagine, it's a little less interesting, but if the phase shift is very large, if, say, it's almost random each time you come around for the next orbit, then you can see some really interesting behavior. The phase shift is largest for small pericenter distance. where you have the strongest interaction, so the most energy transfer. And for high eccentricity, since you want a small pericenter distance, but also a long orbital period, the orbital period comes into play. So that combination is what gives you a large phase shift, which is precisely the combination that you would have for high eccentricity migration. So we can ask how the mode energy evolves over many orbits. And as I mentioned, there's a few types of behavior. So one is if this phase shift is small, then you just have this low amplitude oscillation. So here's K is the number of passages, and then this is the energy that's in the fundamental mode of the planet. And over multiple orbits, just kind of does this gentle back and forth between the planet and the orbit. And it's restricted to small values. Another kind of behavior that you can have, it's a little more interesting, is resonant behavior. So if there is a resonance where the mode period or the orbital period is an integer multiple of the mode period, then you still have this energy exchange, this back and forth, but it's slightly larger magnitude. Or it can be, depending on the system, 10, maybe even 100 times larger in terms of magnitude. And the last is chaotic behavior. It's also labeled behavior too. But this occurs for a large phase shift. So this is the situation where when the planet comes around again, you could model the phase of the oscillation as being random. So in this case, you have diffusive growth in the amount of energy that's in the planet. So this is a way to very rapidly take energy from the orbit and funnel it through the planet. So here, just to give some perspective, the units on the left are units of the initial orbital energy, but this is comparable to the binding energy of the planet. So you might think, well, at this point, that doesn't seem like a linear behavior anymore, and this is a linear treatment. So what we do when the F-mode energy reaches some fraction of the binding energy, then you assume that it's rapidly dissipated through nonlinear effects, through maybe coupling with other modes, or more likely through wave breaking, that kind of thing. So at that point, the energy that is in the oscillation in the planet is very rapidly dissipated within an orbit. So far, this has been a bit abstract, so to make it more concrete, we can map out in terms of eccentricity and in terms of pericenter distance, what kind of behavior do you expect to see for a standard giant planet? And here is this line that divides the chaotic behavior from the non-chaotic behavior. So that's plotted here in color is the maximum mode energy that's reached in 10,000 orbits. So if the mode can reach a very high energy, then you have the chaotic behavior. Whereas if it's restricted to this low amplitude back and forth, then that's shown in blue. And you'll see there's actually a lot of features in there that correspond to many, many resonances. It all sort of washes out in the blue region. But as I said before, for small pericenter distance and for high eccentricity, then you have chaotic behavior. And those are exactly the ingredients that you need for high eccentricity migration. In fact, to the point where if you have a system that can undergo high eccentricity migration within the lifetime of the star, there's a good chance that at some point it's in this area where you should be concerned about chaotic tides. So we can ask how chaotic dynamical tides affect the orbital evolution of a migrating gas giant. And we'll look at two flavors of high eccentricity migration. So the first is von Zeipel-Ledoff-Kozai effect. So far we've just been looking at a system with a star and a planet, and now we'll throw in another star. So here the inclined companion is going to induce eccentricity oscillations in the orbit of the planet. And that looks something like this. So here it may be a little counterintuitively, you have 1 minus the eccentricity, so high eccentricity is toward the bottom of the plot. And these oscillations happen on roughly a megayear timescale. And any time that, and here's what happens when you throw in just standard treatment of tides. So no chaotic tides, just the static tidal bulge. So over time, you can see the semi-major axis will eventually start to decay. And when it's decayed enough, then the eccentricity oscillations will halt or freeze. And at that point, the orbit circularizes to that of a hot Jupiter. But any time that the planet is above that threshold or below that threshold on the figure is a time when it meets the criteria for chaotic tides in the planet. So when we put in the dynamical tides, here's what we see. So here on the semi-major axis, you can see that very rapidly within one high eccentricity phase, the semi-major axis has shrunk, has more than cut in half, and the eccentricity has circularized just a little bit. So we can zoom in to see in more detail what's happening here. So here during this phase, you can see the semi-major axis kind of meandering down over a time scale of 10 to the 4 to 10 to the 5 years. And the orbit circularizes a little bit. And while this is happening, while tides are dominating what's happening with the orbit, the pericenter distance stays roughly constant. And that's due to conservation of angular momentum. There's only so much angular momentum that you can put into the planet. It's only so big. So the pericenter distance for this time frame remains about the same. And this is what's happening to the energy in the mode in the planet, in the fundamental mode, over the same amount of time. So you can see that there are multiple episodes where the energy rises to our threshold. So the threshold is a bit is parameterized, so we choose what the threshold is. And at each of these points, it rises to the threshold and then is dissipated rapidly to a value which is also parameterized as the residual energy. So this can happen, these dissipation episodes can happen multiple times within just one high eccentricity phase. Okay, and then you can also learn something about when the onset and the end of this behavior, just from looking at the conditions for where chaotic tides can occur. So this behavior is self-limiting. It won't continue forever. If once the orbit has decayed enough, then it no longer operates. The orbital period is not long enough to meet the criteria to continue having chaotic behavior. So now we'll go back here and then zoom out a little bit to see what's the longer-term story. So longer-term migration occurs in two phases. And the first is that the chaotic tides rapidly shrink the orbit. And at that point, the planet is a highly eccentric warm Jupiter. So I should point out it's still very eccentric. This is still a planet that's upwards of maybe 0.85 eccentricity. So this is not circularized a whole lot. And then after this has happened, the chaotic dynamical tide is no longer as important. At this point, it's good enough to look at the standard picture of tides of the static tidal bulge, and that will take you the rest of the way to circularization. But this happens more efficiently than the case shown in gray, which does not have dynamical tides, because after one high eccentricity phase, now the pericenter distance is always going to be small. The eccentricity oscillations have stopped and the eccentricity is frozen in. So at this point, circularization is a little bit more efficient. So we can, one of the nice things about this von Zeipel-Ledev-Kozai effect is that we can sample a range of parameters for what we might expect for the planet, the mass of the planet, semi-major axis, and for the companion. So if we assume it's isotropically distributed, the inclination of the companion, and kind of see what types of distributions we get out for the populations of hot Jupiters. And just before we do that, we'll make the point again that this period range of what you expect to see in the hot Jupiter population is set by the process of the chaotic dynamical tides. So here, this dashed line here was a dark line earlier. This is when the process starts, when the planet starts with no oscillations. That's the threshold for where chaotic behavior can occur. And then once you already have some energy in the oscillation, it's actually easier to sustain this behavior. So then this black line here is where the chaotic tides turn off. So the range of periods that you would expect is set by this bottom line is the threshold for tidal disruption. So you wouldn't expect to see any planets below that. And then the outermost semimajor axis that we consider, that criteria for where chaotic tides are important, will set the period for the longest period hot Jupiters. Okay. So here's some of the properties of hot Jupiters that you would expect from this kind of process. We'll just focus on the top row. So this is the columns each correspond to different combinations of mass and radius of the planet. And you can see that these period distributions cluster around a few days and kind of shift depending on the density of the planet. So the less dense the planet is, if you have something that's more like a puffy Saturn, then you would expect to see it at longer orbital periods, whereas something that's more dense you would expect to see a little closer in. One important feature of this mechanism is that it's efficient. If you look at the time that it takes to form a hot Jupiter, this all happens within gigayears, or within the case of the kind of puffy Saturn, within 10 gigayears, so within the lifetime of the host star. And another important point is that this process can save planets from tidal disruption. So if we just ignore the figure on the left here for time, but if you have a planet that's being driven by Lidov Kozai into a high eccentricity regime, and let's say if this process were to keep going without intervention from chaotic tides, the planet would just be driven off the plot. It would be driven past the point of tidal disruption. But instead, chaotic tides can operate to quickly circularize the orbit of the planet and save it from danger. So when I say circularize, that's maybe a bit of an exaggeration. You can see here is 0.95 in eccentricity, but it's enough to save the planet from being disrupted. And so with the nice thing with the Lidov-Kozai oscillations is you can kind of map out in phase space in terms of semimajor axis of the inner planet and the outer companion, where you expect these behaviors to be able to occur. So systems above the black line can be saved by chaotic tides to form a warm Jupiter that becomes a hot Jupiter rather than disrupted. And you can see that some of these blue systems that form warm Jupiters occur in that region that you would expect. So I've talked about one flavor of high eccentricity migration, and now I'll talk about another one. So another way to start out with a planet on a very eccentric orbit. So we can talk about secular chaos and eccentricity excitation. So in this scenario, rather than just having a single planet orbiting a star, you throw in a few other planets as well. So for these systems, it turns out that something called the angular momentum deficit is conserved. So it's additional angular momentum that's required to take the system you have and then form circular coplanar orbits. So it's conserved, but it diffuses chaotically. And as it diffuses, one thing that can happen is that you can excite the inner planet to very high eccentricities. So that's the mechanism that we're talking about here. And this tends to be a bit more abrupt than the Lidov-Kozai mechanism, which I was talking about before. So it's a bit more dramatic in that it will very quickly drive the eccentricity of the inner planet to a high value. And we can see from population synthesis results some similar results to what we saw with the other flavor of high eccentricity migration, namely that chaotic tides can form hot Jupiters efficiently within a stellar lifetime, and also that they can save some planets from tidal disruption and therefore increase the expected formation fraction that you would expect from high eccentricity migration. So this plot on the left is showing you the minimum pericenter that's reached in a simulation that includes chaotic tides and secular chaos. So two different types of chaos here. If So depending on what you choose for your criteria for tidal disruption, you might have 4.5% of the planets go on to form hot Jupiters or are not disrupted, or the 2.1%. So it kind of depends on what you choose for your tidal disruption criteria. And then also to show that chaotic tides can save some planets from disruption. So here's a case on the right where we've kind of zoomed in at the point where this inner planet, shown in blue, has its eccentricity excited to a large value. So with the chaotic tides included, the planet is able to avoid tidal disruption. This is upper black line here, whereas without, hopefully you can see the pale gray line, the planet would be tidally disrupted. And then this is just to show for another look at a broader population. So this is the outcome of a simulation without chaotic dynamical tides. So you have a lot of planets that are disrupted. The cross is below the bottommost green line. But when you include dynamical tides, then you have a lot of planets that perhaps safely form hot Jupiters if you use this more conservative or maybe more generous look at what where the tidal disruption cutoff should be, although still have trouble with the more conservative values for tidal disruption. So this process is a little bit more, a little more dynamic, I guess, than the Lidov-Kozai mechanism I talked about before. It's a little harder to save these planets with chaotic dynamical tides. And I would say it's really necessary to have that effect to save any of these planets at all. So I've talked a lot about what happens to the orbit of the planet, but what happens to the planet itself. So the first thing in figuring out what happens to these planets as they undergo this process of chaotic tidal migration, which implies some sort of dissipation and some sort of tidal heating, is to figure out where the heating should go. So you have some hints of this from Athena++ simulations that Morgan has led in a different context of giant stars that have a companion. So as that go through a close encounter with a companion. So you can kind of see what's happening to the outer layers of these stars as they pass very close at pericenter. And these simulations suggest that a lot of the energy is going to be dissipated in this very thin layer of material on the outer star or the outer planet, by analogy, where the local oscillation speed, of material moving with these tidal oscillations exceeds the local sound speed. So that gives an idea that a lot of this energy is going to be dissipated toward the surface of the planet. So we can model what happens if you have uniform heating in some outer envelope of the planet, and this is parameterized here. So the different panels show different depths of heating, ranging from the deepest heating on the left to the most shallow on the right. So here, the heating only occurs within the outer thousandth of mass of the planet. And you can see that the shallower the heating, the less the radius of the planet inflates. I'll just point out here, though, that it's really only a small layer of mass that's being puffed up. So these lines show here, so this is below everything, like 99% of the mass is below this dotted line. And then all but 1/10,000th of the mass is below this next line. So really it's just this very light, puffy atmosphere that the planet is developing as it's tidally heated. So we can try coupling the structural evolution and orbital evolution. I'll just remind you briefly that in this process, in the chaotic process, there's multiple heating episodes that happen within the time scale of 10 to the 4 or 10 to the 5 years. But that's a little bit difficult to put into something like a simple simulation with MESA or with a stellar evolution code. So we'd like to do something a little simpler. So what we do is we approximate the tidal heating rate with this equation here, where the heating rate is just the amount of energy you would expect to be transferred at pericenter divided by the orbital period. And as long as the heating episodes are frequent enough, then that captures the overall response of the planet. So here in blue is what happens if you have regular episodes of stronger heating, like we saw in the previous plot, and then in red is showing the behavior from the average heating rate. And we can also kind of do the negative to see what happens to the orbital energy, assuming that any energy that you're putting into the planet is coming from the orbit. So the orbital rate of change of the orbital energy, just the same equation as before, but with a minus sign. So when we evolve the orbit, assuming this rate of change for energy and constant orbital angular momentum, then this is what you see, and it's with the dashed blue compared with an actual simulation, which is the black. So it roughly follows the behavior pretty well. So this is what we can put into stellar evolution codes. We use MESA and couple the heating rate with the orbital evolution, so evolve all of that together. So this is what we see in terms of the evolution of the planet radius over a timescale of a single high eccentricity phase for different depths of energy deposition. So the red line is put deeper into the planet than the blue line. And here's the criteria for tidal disruption, shown in black. So we can see that if the heating is shallow enough, then it's possible that many planets will be able to survive this chaotic tidal heating. But I'll point out too that even for planets that are inflated enough to technically pass this criteria for tidal disruption, it's unclear exactly what's going to happen in this situation, if they're really disrupted, or if, I think more likely, it's kind of a gentle mass loss, where they lose some of the mass in the outer envelope. So it'd be a great thing to look at more with numerical simulations. And just to show the luminosity that you would expect for this planet will rise to the tidal heating rate. It's sort of what you would imagine. The tidal heating rate is much larger than the luminosity, or can be much larger than the luminosity of the planet. But this episode is really brief. It will only last as long as the heating phase, and then it will come back down very quickly. So in order to see this, you really have to catch it in action.
So is delta M, how deep you put the energy, is that something you guys just vary by hand basically, or what's the, how do you decide like how deep it should go?
Yeah, so it's something we vary by hand. I think that in order to really decide where that should be, you'd want to have some kind of numerical simulations to kind of back that up. But in general, the big range that we're looking at of like 10 to the minus 3 or thereabouts, I think is probably about right in terms of mass. But yeah, that's definitely a fuzzy factor with this.
Thanks.
And the last thing I'll talk about is the expected liquidity distribution for these planets. So just in case I haven't said it already in the talk, when I talk about obliquity, I mean the angle between the orbital angular momentum of the planet and the stellar spin axis. So many hot Jupiter hosts have high obliquities, and recently there's been some discussion about a preponderance of perpendicular planets. So this kind of clustering of planets with obliquities around 90 degrees. And these aren't all giant planets shown in the plot, but a lot of them are. So we asked, can high eccentricity migration explain perpendicular hot Jupiters? And high eccentricity seems like a more promising place to start than other formation theories, like disk-driven migration, because you can imagine with disk-driven migration, it might be a little harder for things to become misaligned. So here's from that paper that I referenced earlier, the Albrecht paper. You can see sort of from different simulations of high eccentricity migration, what you would expect the obliquity to be. So the one that I was talking about earlier would be the COSI, which is shown in red. And at first glance, no single migration mechanism works. In particular, this one seems to miss out completely on this population, this perpendicular population here, that it would be interesting to explain. But fortunately, there's a lot of things that can go into the final obliquity you would expect from the hot Jupiters. I'll explain why this obliquity distribution in red is a little bit misleading. So here we have, just to go over the von Zeipel-Leadoff-Kozai mechanism again. You start out with a cold Jupiter orbiting the star, and then you throw in an inclined companion. And in a lot of previous population syntheses, the assumption is that you start off with spin orbit alignment. So you start out in a place where the orbital angular momentum of the planet is about lined up with the stellar spin axis. But we actually know that that's not a great place to start. So cold Jupiter hosts, which is where your starting point for high eccentricity migration, can obtain a large obliquity. And the reason why that is the real starting point of the system has a protoplanetary disk. So there's a precession frequency associated with the oblate star and also one associated with the disk. And initially, the disk is going to be much more important. It'll be a faster precession rate. But as the disk goes away over time, then that will no longer be true. And you move through a resonance crossing between these two precession frequencies. And that's a way to excite a high obliquity in the system. So to start with a misaligned system before eccentricity oscillations even begin. So if we, instead of assuming initial alignment, primordial alignment, use simulations of, or kind of an analytic calculation of what you would expect the obliquity to be as the disk dissipates over a set time scale, then you come up with very different predictions for the obliquities distributions of the hot Jupiters. So here on the left, it was similar to what we saw before. This is a little bit of a more restricted population synthesis, is why it doesn't look quite the same as the previous plot. And then here on the right is when you start with primordial misalignment. So here you have this cluster of planets with a polar alignment. And then it's possible that for some of these systems here that are retrograde, that over time, tidal dissipation in the star, so I've been talking about the planet, but now tidal dissipation in the star will work to realign to a polar alignment. So that's one of the things that can happen in principle. It needs to be kind of demonstrated that these systems could actually realign to polar. But the main point is that when you start with a more physically accurate starting point for the system, then you can actually get a population of perpendicular planets from this type of high eccentricity migration. So in summary, eccentric gas giants can undergo rapid, significant evolution due to chaotic dynamical tides. And this process helps a lot of these planets to survive tidal migration, although it's unclear if some of them might be stripped of their outer layers as they migrate. And this brand of high eccentricity migration with the inclined stellar companion that induces eccentricity oscillations is not actually at odds with the preponderance of perpendicular planets. So, thank you.
Some of the same mechanisms that you described could be applicable to dwarf galaxy satellites of galaxies, because they also go through tidal disruption, and you might have similar phenomena that save them. And as far as I know, in the galaxy evolution literature, that was not discussed.
Oh, huh.
So it would be interesting for you to consider under which circumstances you can avoid destroying the satellites. Maybe we can see some galaxies. I mean, we do see perpendicular rings. We do see that of stars. And all kinds of phenomena that you described here, but in the context of galaxies.
Oh, that's interesting, yeah. I thought about that, yeah.
So you described that a small amount of the mass of the planet would be brought out to larger radii.
Right.
And of course, the radius inflation of hot Jupiters is a long-standing question. I was just wondering, when you did you have a chance to calculate? You know, those observations are done with transits. Did you have a chance to calculate at what radii those mass distributions would be opaque? So what would be the transit that the observers would actually infer?
Oh, I see.
Yeah.
No, I haven't
Okay.
looked into that. Yeah.
There's some
Yeah.
public codes to, you know, it's not, and
Yeah.
so, but that'd be really, really neat to then connect it to the observations, because of course, you know, if it's a very small amount of mass, actually it would be
Right.
transparent.
Right. Yeah.
Yeah.
Exactly.
Okay.
an interesting point, yeah.
I think it's still that outermost radius because I think that's the MESA-defined like photosphere of that object.
But you were using MESA?
Yeah, so this is or MESA for, for the tidal heating,
Okay.
right?
Yeah, I mean, it's not the photosphere, because the transit radius is actually well above the photosphere usually,
Okay.
because you have such a long path length.
I see.
Matter goes a long way.
I see.
Interesting.
Yeah.
Okay.
Yeah.
This
yeah,
would be, as an observer,
yeah.
right, it'd be really curious to know
Definitely.
what the actual.
Right, what the
observed
implications
on.
are for the transit while that's happening, yeah.
And I think the thought is these things might have like either a very large scale height atmosphere or like even maybe a thermal wind coming off of them. Like, so maybe that changes their apparent.
Well, then the mass loss will also be really neat. That is observed,
Yeah.
right? We do see these tails for some Jupiters.
Yeah, so that's something I'd be really interested in following up with.
But
is
they're
actually-
generally circularized, so I don't know
Yeah.
if they would still be losing mass at that point.
Right, so,
People haven't done it for the, you know of any that have been done
yeah.
for very eccentric Jupiters?
yeah.
Yeah, neat, okay.
What might be the impact on the star?
Right. So there was one thing I haven't talked about as much. So it depends on the mass of the planet how much the star is affected. If the star can also have some kind of important effect from the planet exciting oscillations like dynamical tides in the star. So I think if the planet is approaching more like 5 Jupiter masses, like that's sort of the range where tidal dissipation in the star can be important for the system as well. While the planet is in an eccentric orbit, it could excite oscillations in the star depending on if there's a good alignment between the frequencies of oscillations in the star and the frequency of that passage. But I'm not sure that they would be large enough in amplitude to see while the planet is still kind of in its eccentric orbit. So I'd have to think about, I think that would depend on the structure of the star.
Because all of this
Yeah.
is done like in the first 20 million years.
Yeah, this is
Right,
all
so-
very fast, yeah.
Okay, I just wonder if there would be, and we see a huge scatter
Yeah.
in initial rotation periods of stars at those early years as well, and I wonder if there's a signature
sure.
that might be impacted.
Yeah, that'd be
later on in
interesting
life.
to see. I think my intuition is that it would be a relatively small effect, but I know one thing that I didn't talk about is the rotation rate of the planet. So in this work, we assume that the planet is rotating pseudosynchronously according to like weak tides, the standard tidal bulge prescription. That's not actually self-consistent, and that it could be rotating significantly faster for the dynamical tides. So it's something that's been on the list of things for a while. At some point to go back and like self-consistently track the spin evolution of the planet as well.
Yeah, actually, just picking up, I mean, I would
Yeah.
expect them to be spinning at like 10 hours, just from
Yep.
conservation angular momentum, look at Jupiter and Saturn.
Right. Mhm.
So,
Yeah.
would they really be spun down to the pseudosynchronous period so quickly?
Yeah, so I think so the pseudosynchronous rate for the dynamical tide can be a significant fraction of the critical rotation period for the planet. But it's unclear if it actually will reach those rotation rates within the time frame of the evolution. So you
Right.
can only adjust so much within each pericenter passage. So I'm not sure.
I have questions.
No.
I don't even ask you.
So, what kind of outer planets or tertiary stars do Jupiters have to have for this to work?
Right, so you want something, so it has to be highly inclined in order for the coside mechanism to operate. So it has to be a larger mutual inclination than about 41 degrees. And you need something that is in the range of maybe like a few hundreds of AU, something like that. So it's sort of what you're looking at. And there's one thing that I didn't mention. So there aren't, there are a lot of hot Jupiter systems, like even the ones with high obliquities, don't seem to have companions within that range. So this is just kind of one type of mechanism that could be forming the hot Jupiters, but you would need other things as well.
Or just something low mass that you can't see, right?
Yeah, yeah. Yeah, that as well. And then another type of, another situation you can have is where a distant planetary companion is actually responsible for the eccentricity oscillations. So we just focused on the stellar companion, but you could look at the planetary companion as well.
So for COSI, so you have two models. You have to start with the high eccentricity.
Yeah.
So one idea is COSI, and one idea is this like planet-planet scattering.
Sure, there's yes, yeah.
And then you may have showed this, I think you did, but how often does COSI give you the really extreme eccentricities that you need? You need like 0.96, right?
Right, yeah.
Right. And how often does planet-planet scattering, you know, I could see that giving.
Yeah.
But I just was wondering quantitatively, how often do you get to the really high eccentricities that you need, not just eccentric?
Yeah, so I'm trying to, I can't remember the exact rate of, well, maybe I do, things that are, like, that includes disruption and hot Jupiter formation, so things where you reach a high enough eccentricity for something to happen. I think it's around, like, 15% of the systems that we looked at in our population synthesis meet that criteria, like 15 to 17%. It's a lot more common actually for systems to be disrupted than to successfully form a giant planet.
Disrupted meaning
into
the star?
Yeah, meaning the pericenter distance is too small. They're just torn to shreds. It's actually, a lot of it depends on the time. So once you include higher ordered optical effects in the lead-off COSI, then a lot of systems will, given enough time, reach very, very high eccentricities. But it's not all of them will within kind of the time frame of the lifetime of the star, the lifetime of the system.
Yeah.
So, yeah.
And for the planet-planet scattering?
I'm not sure for the planet-planet scattering. Yeah, I'd have to look. And then for the secular chaos, yeah, I'd have to check back to see what the rate was for, for how many things reach a small enough pericenter distance for something interesting to happen.
Because it would be really neat, you know, we know the rate of occurrence of hot Jupiters really well, finally.
Yeah, yeah.
And so it would be neat to see if you get that. It's like 0.5%.
Yeah. Yeah, I think at the time of the first paper, I think our optimistic estimate was this could account for maybe like 20 to 30% of observed hot Jupiters, but that was a pretty optimistic estimate. I'd say it's actually probably a little smaller than that. But that's both our understanding of hot Jupiters and kind of the theory has changed a bit since that paper came out. So.
Yeah, the rate of occurrence of hot Jupiters has gone, the kind of observational rate has gone down.
Right.
For metallicity effects. So the actual number now is like 0.5%.
Okay,
It used to be like 1%.
Yeah.
So maybe that's 30% you needed.
Yeah. It's, personally, while I obviously have a lot invested in this mechanism, I'm not morally opposed to other hot Jupiter formation mechanisms operating as well.
So other than seeing a like tidally glowing eccentric hot Jupiter, are there any, do you think, like lasting after effects that on, say, an individual basis rather than a population basis, could you ever imagine saying like this particular hot Jupiter must have come from the high eccentricity pathway?
Yeah, I think that's a little bit tricky. One thing perhaps that you could look at is if you have a system where you know that you could rule out kind of other close planetary companions, where you can identify a likely suspect for like a stellar or a wide planetary companion, like those kinds of situations, then, and if it has a high obliquity, then you could say like, okay, circumstantially this looks like it's more of a candidate for coming from this mechanism, from the high eccentricity migration than through something else.
Well, does then the fraction that are oblique tell you something like, like, I don't know exactly what that fraction is, but then combining that with your like sort of probability distributions, does that give you an estimate of the population fraction that are coming from a channel like this?
I think it does give some insight into that. So there is also a body of work looking at how to generate, systems with high obliquity or high-ish obliquities through disk-driven migration as well. So it's kind of another component. But yeah, I think in general, the systems with high obliquity are more of a suspect for high-eccentricity migration. I think Melina Rice has some recent work on this, kind of looking into things from that perspective. Yeah.
Okay. Awesome.
So the thermal evolution could be quite distinct, right? Because you are heating, in addition to the stellar heating, there is significant heating. So that if you know the age of the system, you could compare that to what you expect for a cooling Jupiter, and perhaps learn about additional heating.
This is true. I think one thing that's tricky with the heating is that the heating for this process is so rapid, and then the planet is able to cool back down so quickly that it's a little difficult to catch in action. But if maybe there's something that happens throughout the process, like you're more likely to lose some mass in the envelope, like that's something that potentially we might be able to look at later.
Yeah, I mean, the fact that most hot Jupiters are signal that's a lasting observable for sure.
Right.
But some are not, like WASP 47
Yeah,
is this like, stupid little planet tucked in. So, it's a mystery. Finally, there are Neptunes and Jovians being identified at comparable ages where your effects are happening. That's coming from TESS observations of moving groups. So we are getting some findings that are like 10 or 20 million years old.
Oh, okay, that's really interesting.
And not much follow-up has been done, they've just been discovered.
Yeah, because I'd be very interested to see, like, as we have a better understanding of the ages of these systems, like what kinds of...
So there you would know, the ages really well, because you're in a
Right.
moving group and you have more massive stars where you can really get that age.
Sure.
Would those systems have different semimajor axis and eccentricity distributions in your view, because they haven't undergone the slow, weak tidal phase that circularizes them eventually?
Yeah, I'm not sure. So I think for the younger systems, like if you're kind of catching this process in action, you'd be more likely to see planets that still have some eccentricity. And then also I think the migration on average is going to be faster for the more massive planets than for the less massive planets that tend to form at longer periods. So maybe you could see something there as well.
You probably have enough targets now to do a statistical example, right? Like we're in the 30s to 40s of transiting young planets that are confirmed. I guess there's lots of post-candidate data mentions. But that seems like enough that you could do a comparison to the older sample. That'd be fun.
Yeah.
That's amazing.
Yeah.
Well, I think we have time for either one more question or to thank Michelle again. Let's thank Michelle. Thank you. This is really wonderful.